Hi everyone, welcome to these Python tutorials where we are putting special focus on image processing related tasks. In the last couple of videos, we have been looking at various terminology that gets used as part of deep learning. In the last video, we looked at loss functions, and in the one before that, we looked at scaling. And in this video, let's focus a bit on backpropagation and optimizers. And if you understand this topic of backpropagation, I should say you're one of the lucky few who actually understands what's going on as part of deep learning. Okay, so let's jump in and get a bit of an understanding of backpropagation and optimizers, and jump onto our Google Colab to play with a couple of optimizers so we understand it a bit better. Okay, I should warn you that this is not an easy topic because technically backpropagation involves heavy math, understanding gradients. I'll make sure that we don't use a lot of math, but yet you understand exactly what's going on as part of backpropagation for those of you who probably haven't taken a math class in a long time. Okay, so let's jump in. First of all, let's get a high-level summary of what's going on with deep learning, right? I mean, the essence of deep learning is to find the best weights, right? You have a network, and what are the right weights that can map your input to the output, right? That minimizes the loss functions. So we are adjusting the weights so the loss function is minimized, and wherever that minimum is, this is our solution to the problem. Okay, now how do we do that? This is an iterative process. We first adjust the weights and look at the loss function, and then say, okay, let's change the weights and let's look at the loss function. If the loss function is heading in the right direction, meaning as it's going towards finding a minimum, we are heading in the right direction, right? So that minimizes this loss. So let's keep changing the weights until the loss function gets to a minimum. So to find this direction, we need to find the slope of the loss function, right? I mean, we have to find the slope so we know which way we are sloping. We don't want to go the other way. We want to go towards the path that takes us towards the minimum in this loss function. Okay, so we have to find the slope, and this is achieved by computing the derivative, or gradient if you want to call that. I'll get to this in a minute, but let's just establish at a high level the process. Next, it's of course computationally expensive to compute derivatives for millions of weights. The scenario I just explained, how the loss function changes as you change the weight, is for one weight, but your network probably has millions of weights. So how do you change these millions of weights and with respect to the loss function, right? This can be very expensive when it comes to computation. So there is a trick called backpropagation. So the term backpropagation refers to this trick of making the computation possible to finding these derivatives. Okay, and this is just a mathematical trick. It's called chain rule in calculus. Again, I'll briefly mention about this, and the essence of this is finding the derivative of loss. Right, the loss function. Our main goal is to minimize the loss function with respect to weight. So it makes that possible for every weight in the network. How does it do that? By backpropagating. We'll get to that in a minute. Now, you'll also hear the term called gradient descent. In general, gradient descent, I mean, sometimes gradient descent and backpropagation are used interchangeably. I don't see much of an issue with that, but just to give you an idea, gradient descent is a general term for calculating the gradient and updating the weights. So what are we doing? We're trying to find the gradient so we know which direction to go, and then we update the weights so we are heading in that direction, right? So that process is called gradient descent. Okay, we are descending using the gradient. That's what this is. Now let's get to the next level. Actually, again, I used this graphic in the video where we talked about what is deep learning, so it's worth repeating because I think illustrates the process a bit better so we can move forward. Okay, so you have an image, and the goal is to train a network to find out if this is a mitochondria or a lysosome or something else, right? So, okay, there is an input layer. A bunch of inputs go in. Typically for images, of course, this is going to be your pixel values. And the next is the hidden layer 1, hidden layer 2, hidden layer 3. And if it is fully connected, everything is connected from every artificial neuron, every other neuron in the hidden layer is connected, and so on. Up to what point? Up to the output layer, where you have, in this case, we have 3 outputs. This is a multi-class classification where we are trying to predict if it's either lipid, mitochondria, or lysosome. So if the training works fine, you get, let's say, once you send a mitochondria like this, it says, okay, 92% confident that this is mitochondria, 7% lipid, and 1% lysosome. Right? So this is how it actually works. These are all hidden layers. And why do we have different hidden layers? Because at every layer, it learns something different. At the first one, it learns about edges. At the next one, it learns about the combination of these edges, and then the features and so on. Now let's only look at one of these, right? I'm only looking at one of these. So if you look at that, again, this is a bit of a repetition of what we already did, but it's worth it. So now let's look at, okay, for this neuron, artificial neuron, you have a few inputs, and each input comes with its own weight. And all the neuron is doing is multiplying the input with the weight, and adds all of those, and adds the bias. And then we send it through an activation function. Okay, we talked about this already, what activation functions are. And we send this through an activation function that if it is a sigmoid, it brings all the values to between 0 and 1. And you get a probability. Okay, so far so good. Now let's expand this a bit more. Let's actually create a neural network that's small, meaning we have 4 inputs and 2 hidden layers. In the first hidden layer, 3 neurons, and in the next one, 2 neurons, and we have 1 output. Okay, so this makes it a bit easy for us to understand the process here, or to understand the backpropagation process. So we have input, layer 1, layer 2, and output. And all the output values I just gave, OF represents the output in the final layer. O21 is output in the second and the first one. Okay, if you see X1, and then I have output 1, and then output 2, output 3 would have been here, but this is the final layer. Okay, so far so good, I hope. And the weights, again, just so we can keep track of these, I am just using the subscript, from here, and then tagging along to this weight. So this would be W weight 111. This would be weight 1121 because it's connecting 11 and 21 neurons. So this weight would be 122. Sorry, that I got it wrong. This should be 1122 from here to here. Okay. Apologies for that. I should have caught that. And this is 1322. Obviously, as you can see, this is 413. Okay, and this is 22F. There's a reason I'm spending a little bit of time trying to understand this, because when we get to the actual backpropagation part, we'll have to look at each of these. Again, I promise to make this simple. What do we get out of this after applying activation? Basically a prediction, right? So we get a prediction, we call this Y prime. Y is the true label, Y prime is the prediction. If Y is mitochondria, if Y prime, if Y is 100% mitochondria, if Y prime is 92% mitochondria, so Y prime is 92, Y is 100, right? So Y prime is the prediction. Okay, now let's actually look at the loss function. What is the loss function? If this is a regression problem, we would be using mean squared error as our loss function. Again, in the last video about loss functions, we talked about it. It's easy to think in terms of mean squared error, so let's just stick to that for now. Okay, so what do we get out of this network? A prediction called Y prime. What is the error? The error in this case is Y minus Y prime, my true label or true value minus the predicted value, right? This is the deviation from our truth whole squared. Why are we squaring it? Because it could be on the negative side or positive side. The sign doesn't matter. We just look at the square of it, the magnitude of this error. Okay, and then we average 1 over n because we may have like n data points right there. This is our loss function. Okay, if you plot this, let's say your loss function is like this, and if your initial weight, okay, now let's go back. If your weight right here, okay, is 1121, and then you run this network, you get some output here, and then you calculate your loss function. So let's say at that point, at that weight, the loss is, I don't know, 1.6, let's say. Now we say, okay, let me move to the next point, and then we come back down here and we decrease, we change our weight from whatever that value is to this value, and then we calculate the loss again, right? So every time you change the weight, you're actually getting a new output, which means you're actually getting a new prediction. If you have a new prediction, you can calculate the loss. right? Once you have your prediction. And that loss tells us, okay, this time our loss is 1.4. So we went from 1.6 to 1.4. So we know that we are heading in the right direction. Next, change this weight again by a little bit until when? Until we find this point, the bottom point, right? This is where I know that I have the optimal weight that gives me the lowest loss possible. Okay, this is again just a repetition of what I've done in the last video where we talked about loss functions. The whole point of loss function is it kind of tells us map this error function so we can actually update the weights and see if we are getting in the right direction. Now the big question, how are the weights updated? I mean, if my weight right here is 25, now do I just go down to 20, or do I go down to minus 200? Or minus 300, or if I'm here, like, I mean, in fact, we are increasing the weight here, right? Is it 1000? Like, by how much should we be changing the weight? So that's where backpropagation comes into picture, okay? But here the key question is, how are the weights updated so we can find this global minimum, okay? So now let's go to the next level. A quick calculus lesson. Okay, so we can understand the slide after this. The calculus lesson here is, if you have some sort of a function, some sort of a graph like this, okay? Now you would like to find the slope at a given point, right? The derivative is nothing but the slope of a function at each point if you draw a tangent line, okay? So this is the slope at that specific point. If you have the data point right there, the slope is right here. So by looking at the slope, you know how steep the slope is, right? And you also know whether you're going in this direction, or if this data point is right there, whether you're going in the other direction, right? Whether the slope is positive or negative. That's what we can see. Now, what happens if you're down here, where the slope is a very small value? That means you're not changing much. It's almost like you're at the bottom. Okay, so a derivative is the slope of a function at each point. I'm pretty sure most of you know this. A multivariable function, which means in this example, we are only looking at loss as a function of a single weight, but we have millions of weights as part of our network, which makes this loss function a multivariable function. It has many variables, right? So here, the derivative of the function with respect to a single variable. For example, you have weights W1, W2, W3, W1 million, right? All the way to 1 million. If you look at the change in loss function as a function of a specific weight, like W1, by keeping all the remaining weights constant, this is where you call a partial derivative. A full derivative means the function's derivative with respect to all the variables that you have. A partial derivative is where you're calculating the function's derivative with respect to a specific variable by keeping all the others constant. Okay, that's called partial derivative. Just a quick introduction to terminology. And the gradient of a function. Now let's talk about the gradient. Now we are slowly introducing the gradient terminology. Gradient is nothing but a collection of all of these partial derivatives into a vector. Now you have like W1, W2, W3. So just get your partial derivative of loss function with respect to W1, partial derivative of loss with respect to W2, with respect to W3, and so on, and collect them together as a vector. That's your gradient. Okay, so now just quick terminology. Again, I know most of you read papers, technical papers. So here is a quick terminology. Again, I'm pretty sure most of you know, but it's worth repeating. Okay, dl over dw derivative, this rho L over rho W, or dou, sometimes you call this, over dou W1, depending on which country you're from. And this is partial derivative, and gradient is always this del and L. Okay, so this is how gradient is represented. So okay, now that we are done with our quick calculus lesson, let's go to the next step, which is understanding the backpropagation. Okay, so far so good. We know these are all weights. We know this is the output, and this is the prediction that we are getting, and we know that there's a loss function that tells us how large of an error we are dealing with. Okay, the whole game is decreasing the loss. Now let's look at how to update this weight. Okay, right now I have this weight as some value. In the next iteration, how do I update this weight? Okay, now let's get to the key equation here. The next weight or the updated weight is equal to my old weight from the last iteration, right? My old weight minus this value. That's it. So my updated weight, the way the weights are updated is basically the old weight minus some value. Now let's understand this. This multiplication factor is called learning rate. Okay. Again, I talked about this in the last tutorial. If your learning rate is too high, okay, then you'll do things very fast, but then you may not find the actual minimum in the loss function. And I'll show you a quick graphic talking about that. But let's not worry about learning rate for now. It's just a constant. Okay, nothing. This is not affecting our calculation in a way, let's say, because this is just a constant that we can change anytime. Let's understand this. What this is telling us is this is obviously a partial derivative of our loss function with respect to this weight. That's it. Okay. And we know this updated weight. We are calculating this by taking the old weight. We know what that is. We know what this is. We need to calculate this. Then we'll know what the updated one is. That's it. Now, how do we calculate this? This is where the chain rule comes into picture. Now think about it. And the weights are updated from right to the back. And we'll see that in a minute because we know what the new output is, which is a function, which is a function of this output right there. And this is a function of the weight. And once we know this weight, we can go back and update this weight and then update that weight and so on. So you're doing this from right to left if in this graphic. Okay, so that's why it's called backpropagation. Now let's get to the next equation again. Let's understand this in plain English and then get to the equation. Okay, so updating the weights, right? When we change the weight, it results in new output. Correct? We change the weight, we get a new output, which in turn yields new loss value. Because once you get a new output, you're putting it here and then you get a new loss value. So obviously loss is a function of weight, but loss is a function of output, which is a function of weight. Remember this. This is exactly what we're going to use right now. The level of adjustment is determined by the gradient of the loss function with respect to network weights. We already established that right here. The gradient of loss with respect to weight. But weight is a function of output, or output is a function of weight, sorry. This is where the chain rule comes into picture. I hope you're not confused. We'll get to this in a second again. We'll spend a few more minutes, so hopefully it makes things a bit clear. So chain rule is breaking the derivative of loss with respect to weight into individual partial derivatives of loss with respect to output and output with respect to weight. Now let me put this in the form of equation so we don't have to use so much English. All we are saying is the loss function, the partial derivative of this with respect to this weight is nothing but the loss function with respect to output and the output with respect to weight. That's it. You see how we are doing this backwards? Now let's go to a different example. Now let's pick a bit more complicated one. Okay, there's a lot of calculations going on as you can see, but let's understand this one. Okay, so how do we update this weight? Okay, same equation. The new weight equals to old weight minus learning rate times the partial derivative of loss with respect to this weight. Now let's break this loss with respect to this weight into individual partial derivatives. Okay, this is loss with respect to output from here, and this output with respect to the previous output because that affects this, and this output with respect to weight. So you go from the right, okay, and then break it down into individual partial derivatives and accumulate them so you can actually get your updated value right there. And once you know this is just a simple calculation. I hope this makes sense. And it can be more complicated, okay, if you go through from here to this path to that path. I just showed you one path. It calculates this for all the paths and adds them together. But the key point I'm trying to make here is this is called backpropagation for a reason, because you're actually coming from the right and going towards the back. Forward propagation is easy, right? I mean, once you have your x1, x2 and weights, we saw in the previous slide, this is nothing but this value, x1 times weight plus x2 times this weight plus x3 times that weight, all added together, you get this output right there. Forward propagation is easy. Backpropagation involves these gradients or calculation of these gradients. This is why it's called gradient descent, because once you find the gradient, you are moving in a direction, you're updating the weights in a direction that brings you closer to the minima in this loss function. This still may be a bit abstract for most of you. I really encourage you to read more blogs, more papers, whatever, watch more videos, but this is key for you to understand backpropagation. Okay, I hope you have some understanding right now. Now let's actually visually look at the loss function, like again a single weight right here. Okay, so what we are trying to do is, okay, here is our random initial weight, right? I mean, how do we start off with weights? You start off random initially. I'll talk about this again in one of these tutorials, but we start off somewhere and we calculate the loss. Then we find out, we do this math, we find out, okay, the next step is right here, and the next step. How big of a step do we take? You see, that depends upon this multiplication factor called learning rate. If this is large, then this step is pretty large. What you don't want to do is go from here to there because the step is too large, right? So learning rate is a key hyperparameter that you need to kind of tune sometimes. So this is our steps. Now, what happens if you choose a very large learning rate? For example, if you take a very large learning rate, you go from from here to there to here, and you'll never find the true minimum because your learning rate is too big. What if the learning rate is too small? If the learning rate is too small, you're taking tiny steps, okay? Which is good if you find, if you are in this area, if you're in this area. But if you're right here, this loss surface is not like a very nice smooth curve. It can be very complicated. So what if you find a false or a pseudo minimum instead of a true global minimum? This can be an issue if your learning rate is too small. Okay, so I hope this makes sense, and let's look at this in a 2-dimension, right? So if you have on x-axis, let's say you have weight 1, and here you have weight 2, and this is the loss. So what happens when you're changing these two weights? And obviously we're dealing with n-dimensional space when you're talking about real life weights, right, in neural network. So let's say we start off right here, initial weight. If you're lucky, you just go this way and then find this local minima. I mean, if you're lucky, you would actually go all the way here and then find this global minima. But if your initial weight is right here, there is no way that you can actually go down all the way down here, right? There is also a good chance that you just keep updating the weights like around here, and then you'll never find even the local minima, but then you get stuck like right around here. These are all real case scenarios. That's why I'm just visually showing you what could happen when you're training your deep learning. And let's say our initial weight is right here. So initialization of weights is very important actually. And we'll talk about that in one of the upcoming tutorials. So if you start your weight right there, well, it can actually go this path and find a minima right here, which is not global minima, but it's not a bad solution. I mean, it's going deep enough, right? Or if you're lucky, it just goes around this and then finds you the actual global true minima for this loss function space right here. So I hope this makes sense. I hope this makes you understand what backpropagation is, first of all, where we are using the trick of math, calculus, the chain rule, to break a complicated derivative into a series of partial derivatives that we multiply. Now, one thing you should realize, I should have talked about it. Here, you see, this is just a multiplication, right? So what if these values are too small? What if every time you update this, they're getting smaller and smaller? What happens if you multiply 0.1 multiplied by 0.1 by 0.1 by 0.1? By the time you get here, the weights could be like, the change in weight could be like 0.000001, which means it's insignificant. So the weights are not updating much. This is called vanishing gradient problem, which means your gradient is vanishing. Your weights are not updating because the gradient is near 0. This is a real problem for certain aspects. For example, if you're using sigmoid or tanh as your activation in the inner layers, this can be an issue. That's why we use something called, we'll get to that in a second, okay? But think of vanishing gradient, okay, as one of the problems that you can encounter if you're using sigmoid. But no one uses those anymore. By the way, I almost said ReLU. I thought we already talked about activation function, so I'm just saying it. If you use ReLU function, then as your activation function for inner hidden neurons, then that minimizes that vanishing gradient problem. Okay. Now let's come back and try to understand how to get out of one of these local minima if we end up getting to this local minima. For example, this may be too deep, but there is some local minima like right here, for example, or somewhere over here. How do we get out of that? Now, so to our term where we had like the learning rate, right? I mean, we had this learning rate here. Instead of just learning rate, if we add a momentum term, right? Lambda in this example is a momentum term. This helps us push this a bit forward. Momentum is basically that, right? I mean, if you have enough momentum, you just find this minima, but then you keep going until you find the global minima. I mean, if you have enough momentum here, you'll probably go up here, but then realize, oh, this is the minima, you come back. So anytime you have this deep, deep areas, valleys, even with high momentum, it's tough to get on and then find the true global minima. But if you have these cases, with certain momentum, we can just come out of it and find a true global minima. I'm explaining this in a visual way, but mathematically, all it's doing is to this term, the derivative term, it's actually adding a momentum term. That's it. And the momentum goes between 0 to 1, and 0.9 is a high momentum, in your stochastic gradient descent, for example. Okay, so that's that. And now I just use the term stochastic gradient descent. What does that mean? Well, when you define a model.compile as part of your, model, right? I mean, you add your model, you add your layers and everything, and finally you get to, okay, I want to compile, and what loss function would you like to use, what optimizer, and what metrics would you like to keep track after every epoch. So optimizer, here is where the choices are. You can select stochastic gradient descent. Atom is very common nowadays, and there are many other ones, but these are two oftenly used or very frequently used optimizers. And let's use these two in Python in a minute, but let's understand what stochastic gradient descent is and what the advantages of Atom are, and then switch to our Python code. Stochastic gradient descent. In gradient descent optimization, we just talked about gradient descent. What is it? You're calculating gradients, and then you're descending into the right direction, hopefully, to find the minima in your loss function. So the weights are updated incrementally after each epoch, right? What is an epoch? Again, I'll talk about this in future, but for now, an epoch is you have 10,000 data points. When all the 10,000 data points go through the feed forward, right, where you're multiplying weights and input values, that's feed forward all the way to the end of the network, and one backpropagation, meaning you're updating the weights after you calculate your output and then loss function and then the gradients. You do that. So that's one epoch, when all the 10,000 data points that you have go through this journey. Okay, so in gradient descent, the weights are all updated incrementally after each epoch. So once all the 10,000 points are gone, then it updates it. In stochastic gradient descent, it's not that, which we'll see. But for large data sets, this is computationally expensive. If you have like, let's say 1 billion data points going through, this can be computationally very expensive. So what happens in stochastic gradient descent is the weights are updated after each training sample. After each sample goes through, you get the weights updated, and you can choose a mini batch instead of a training sample. You can just say, okay, only 16 data points or something. But the idea is the weights are updated not after all the data goes through, but then after a small subset of that data goes through this entire journey of forward and backward propagation. Okay, that's the key in stochastic gradient descent, which means by nature you'll have some error, because you're not the network is not seeing the entire data. but still this works. It refers to the fact that gradient is based on a small sample. We already talked about it. And it's a stochastic approximation of real gradient, right? This is where the term stochastic in general refers to random, okay? Approximation of the real gradient. So if you have a real gradient, you'll only find out the real gradient if all data goes through that. But then we are not doing that. We are only sending a small one. And we are saying, oh, that's approximate to the real one. Okay, that's where this term comes into picture. And because it's stochastic in nature, the path towards the minimum can be very bumpy. You see how bumpy this is, but it sure heads in the right direction, given enough epochs. So this is stochastic gradient descent, and there are a lot of variations of stochastic gradient descent, and ADAM is one of those modifications, or it actually uses the stochastic gradient descent, but there are certain advantages. And I'm taking certain excerpts from this paper published by the original authors there, and ADAM is derived from adaptive moment estimation. And here are the key benefits of ADAM over stochastic gradient descent. Computationally efficient, we love that. Little memory requirements. I think these two kind of tied together. Well suited for problems where you have a lot of terms or parameters that need to be tuned. Like, for example, convolutional neural networks like VGG or something. You have millions of parameters that need to be tuned, and ADAM can be very beneficial. Again, why and how? If you're really interested in this, please go ahead and read this paper. And it's appropriate for problems with noisy or sparse gradients. And hyperparameters have, in this case, intuitive interpretation. Like if you look at, I'll show 3 or 4 hyperparameters right now. They make sense when you look at those. It's not like, oh, give me beta value, give me delta. I hate those type of hyperparameters because I don't know what that means. Okay, and gradient descent uses a constant learning rate. This is important. So when your learning rate in gradient descent is constant, in ADAM it computes adaptive learning rate, because initially when the slope is high you would like to take bigger steps, but when you're coming to the shallow part you might want to take smaller steps. So ADAM apparently does that. So here is again from the original paper showing that, okay, ADAM of all the choices, AdaGrad and others that are all in a way kind of based on stochastic gradient descent, ADAM seems to be the one that is performing the best. And some of the hyperparameters, again, here you have beta 1 and beta 2. I'm not a big fan of these type of this type of terminology, but then learning rate obviously makes sense to us. And again, go ahead and read the paper to understand what these are, but apparently these are very intuitive in terms of why you need beta, why you need beta 2. But almost everyone uses the default hyperparameters. Unless you're doing some sort of a research in deep learning, I don't see a strong reason to change, especially the beta values and epsilon and dk. Even the learning rate, you can just leave it at 0.001. Okay, so this is ADAM, and now let's jump into a few lines of code that I'll share with you, but then I just want to demonstrate the effect of learning rate and possibly the effect of momentum in terms of our ability to learn, meaning looking at the loss functions. Okay, so let's jump onto our Colab. Okay, so here I'm using the same example of breast cancer Wisconsin dataset, where it's just an Excel or CSV file, I should say, that has a whole bunch of columns, and one of the columns is diagnosis, which is this a benign or malignant? Okay, and this is our prediction. This is what we are trying to predict, and these are all the attributes or features, if you would like to call them. Now let's go ahead and connect the runtime first. And let's run line by line so we can look at this and not spending too much time. We've already talked about this quite a few times. Importing the right libraries. I'm importing my CSV file. Again, I connected this to my Google Drive, so I can just store my files on Google Drive. And let's go ahead and describe this. You see, we have radius, texture, and all of these, and the values range from hundreds to 100th to 1000th. So we need normalization or scaling, I should say. So let's go ahead and do that. And I'm going to rename my diagnosis column as label, so it's easy for us to interpret. And let's go ahead and plot to see how many of each data points we have. We have about 200 malignant and 350 benign. If you want, you can go ahead and balance this data. but let us encode the labels. So what I'm trying to do here is instead of M and B, I'm just changing it to 0 and 1. That's it. Okay. So my M is going to be 1, my B is going to be 0. I'm just using label encoder, so we can work with these in fitting this data. Again, we'll get to these if anything doesn't make sense, possibly because we haven't talked about them. Okay, but try to follow this, and repetition is the best way to learn things. Okay, now let's go ahead and define our X, which is every column except for these two, label and ID, right? I mean, these are all the attributes or features. Now, what is our prediction? Our prediction is going to be our, meaning our Y is basically the label column, which we'll define in a minute. I thought we already did that. Yeah, sorry. I didn't mention this. We already defined our Y right there, which is our label. Okay. Now, our values are all over the place. So let's go ahead, and because you see we have 654 here and 0.06 here, 880 here. So we need to bring everything. I hope you watched my scaling video, so this makes sense. So I'm using min-max scaler, as we already established as part of that video that this is one of the better ones. So all the values are ranging, are in a similar scale. Okay, let's split our X and Y, I mean testing and training data sets, and let me go ahead and import the sequential, dense, and activation layers from Keras. And here I'm defining two optimizers. Okay, one is stochastic gradient descent, which is part of Keras.optimizers, and the other one is Atom, which is also part of our Keras.optimizers. And here you can change the learning rate. And for stochastic gradient descent, you can also change momentum. For Atom, let's just change learning rate and see how things make sense. First of all, let's go ahead and start with optimizer 1 with a value of 0.01. This is a small learning rate, but not too small, I believe. We'll find out. Okay. And let's define a very simple model. I'm using sequential method, and I'm adding a dense layer with 16 hidden neurons. And then I'm going to drop out 20% of them randomly. We'll talk about this. Why am I doing this? And then my output is only 1, which is just a probability value. If that probability is 0.00 something, then what is it? Then it is 0, right? Then it is benign. If the value is 0.9 something, then it is malignant. That's it. We just need one output. Okay. So let's run that line. We did this right there. Okay, and then finally we are using sigmoid. You see, I'm using sigmoid activation in the prediction layer, but inside I'm using ReLU. Okay, and for loss we are using binary cross entropy because this is a classification problem. And optimizer, let's use optimizer 1 for now, which is stochastic gradient descent. Okay, so let's run these lines. And once this is done, let's go ahead and fit this to 100 epochs. Okay, so there it is. And I turned GPU off because with GPU this goes so fast. I want you to see what's going on the screen, so I turned the GPU off as part of runtime and change runtime type. Oh, it is there, but okay. Let's speed it up. Let's see if it goes too fast. We can change it. So let's go ahead and run this, and yeah, so you see it started off with a loss of, let's go back on the top. I should have actually turned GPU off, but let's not waste time. Okay, it started off with a loss value of 0.733, 0.72, 0.72. It tried to go the other way, but then it said, okay, that's the wrong way. Let's come back, and then other way, let's come back, and so on. So occasionally it goes this, one way or the other, but eventually the trend goes down. You see, it started off with 0.7, and now it went down to 0.52 or something. Okay, so I'll just plot this so you can see how it looks like. You see how the trend is going down, but you see this hasn't converged yet. It's still going down. That's because the learning rate is too small, and 100 epochs is not enough for it to come down and find this minima. So if your learning rate is small, you better look at higher, large number of epochs, right? I mean, here we are doing what? 100 epochs. If you are using these type of learning rates, look at this curve and say, oh, this is not enough. Let's change this to 300, 400, or whatever is required. Now let's come back and change our learning rate to 0.1 and see if that makes any sense. Now, if I run these lines in Google Colab or any IDE, because I use the term model, it starts from where it left off. It starts from loss, like right here, which is normally a good thing. This is how you continue training. But right now I'm trying to compare different things. So this is not a good thing. So what I'm trying to do is runtime, restart, and run all. So it resets this runtime and runs everything from scratch. We can afford to do that because our data is so small. That's why I enabled GPU, I forgot. So we can actually do these multiple times. So you see, it should go pretty fast. And now let's look at our curve as soon as this is done. There you go. You see how nicely it has converged right here. Okay, so even within 20 epochs, it converged. Previously, with our learning rate of 0.001, we were somewhere around here. Right? We haven't found that bottom yet. Okay, so this is why learning rate is very important, and this is an easy example. That's why we are getting like 98% of accuracy overall. But in real examples, you will probably see that, okay, with higher learning rate, you haven't found the global minima. Now, let's change a couple other things. Let's see how, okay, let's leave it at 0.1. I'll let you play with this, but one final thing, our momentum in this case is 0.9. What if I change it to 0.1? Okay, let's again do the same, restart and run all. And I apologize, I should say this is going to be a long video, but I really hope that you understand backpropagation and optimizers, because this is very important for deep learning. Okay, there you go. It just started to converge right here. So I increased the momentum, but it has an effect on the loss. Okay, changing the momentum. It's fun to play with these, actually changing each of these. And now let's actually leave that over there and leave the. Let's run this one more time. Sorry, let's compare optimizer, stochastic gradient descent, and Adam. Okay, let's go to actually 0.001, and let's run this one more time. We did this, but since this is fast, why not go ahead and look at this? I want to now compare stochastic gradient descent with Adam. Okay, optimizers. So let's look at Adam. Should converge. I don't know. We'll see. So there you go. So this is still not converging, right? We saw this earlier. It's still waiting. I think Adam actually converges a bit fast, even for the same learning rate. So let's change this optimizer 1 to optimizer 2 and run, restart, and run all. And after this, we'll end this video. It's already a long one, but like I said, I hope you learned something new. So let's go down. Yeah, you see how Adam is a bit faster in terms of converging. So again, as a rule of thumb, if you don't know where to start, always try to use Adam. And if that doesn't work out, see if something else can help out. Now, how do you know if that doesn't work out? Well, it's partially from experience and partially from watching all of these videos. And when you put all of this information together, the effect of loss function, the effect of initializers, the effect of optimizers, then hopefully you'll have some idea in terms of what to change when your problem is not converging, for example. Okay, so in summary, I hope you understand backpropagation. I hope you understand optimizers. And again, one suggestion is use Adam. And in the next video, let's go ahead and talk about a different term that is essential for you to properly understand deep learning. So thank you very much. And again, subscribe to this channel so you get notified whenever a new video gets uploaded. Thank you.